Welcome everyone, my name is Da Yan. I'm an assistant professor of computer science from the University of Alabama at Birmingham. Today, I will present our paper titled Distributed Task-Based Training of Tree Models, which describes the design of our distributed system named the TreeServer for training tree ensemble models over large tabular data. First, let's review the concept of decision tree and the tree ensembles. Here, we show a data table where each row follows a path from the root of the decision tree to a leaf node, which gives a predict label. For example, record number 5 has A1 less than 40, so it goes to the left child, and since A2 is pitch D, it further goes to the left child, which is the leaf node that gives the prediction no. We can see that each node in a decision tree is associated with a subset of rows in the data table. Decision trees can be used by the idea of bagging and boosting to create large ensemble models that are more accurate. For example, the recently proposed deep forest model can contain many trees, making it important to have an efficient parallel tree construction system. Recall that at each node, we compute a condition to split the rows into the left and the right children nodes. Here we review how such a split condition is calculated. Consider A1, where we try different split conditions and their resulting impurity scores, such as entropy and variance. Here, A1 less than 5 leads to an impurity of 10. A1 less than 10 leads to an impurity of 5, which is smaller. And A1 less than 15 leads to an impurity of 10, which is larger again. So we select the second condition for A1, which has the smallest impurity. We do the same to find the best split condition for A2, A3, and A4. The overall best split condition with a minimum impurity is therefore A2 less than 6. In recent years, there are two trends in building tree models, including building larger and larger models, such as deep forests with many trees, and using scalable distributed systems to build the models from large tabular data using parallel and distributed infrastructure. Our TreeServer system features two designs that are different from prior systems for constructing decision trees. Firstly, TreeServer partitions the data table by columns to different machines rather than by rows as in Spark MLlib or XGBoost. Secondly, TreeServer uses a task-based parallel execution model called Tsinker to make sure that CPU cores in a distributed cluster are fully utilized. Recall that to compute a node split condition, we need to find the best split condition for each column AI. And for each column, we actually need to try many alternative split values to partition the rows. So if the rows are on different machines, a lot of communication is needed for each split value of each column. In contrast, our TreeServer system partitions the data table by columns so that each machine that holds a column AI can compute the best split condition of AI by itself without communication. In fact, existing systems that adopt row partitioning cannot compute the exact split condition due to the overwhelming amount of communication, and they had to use approximate methods to reduce the number of split values that they examine. On this slide, the paragraph on the left shows that Planet, which is Google's tree building MapReduce algorithm and later adopted by Spark MLlib, uses approximate equidepth histograms, while the paragraph on the right shows that XGBoost uses weighted quantile sketches to find good approximate split values. Besides column-based partitioning, the other desirable feature of TreeServer is that it uses a task-based execution model to keep CPU cores effectively utilized. Specifically, when the number of rows falling into a node is small enough, it is more efficient to let a machine pull all those rows to its local memory and construct the entire tree without communication. For example, node X7 on this slide only has 2 rows, 8 and 9. So we let a machine pull these two rows to its local memory to construct the green subtree. Since TreeServer adopts a column-based partitioning, we actually need to pull the columns of those two rows from different machines. Here, our task-based computing model is called Tsinker, and it was proposed early on as a CCC great innovative idea. The idea that if the computation cost is high and superlinear to the data size, as long as the data size is reasonably large, the computation cost would be high enough to justify the linear cost of pulling the data to local memory. And as long as task computation and data communication are properly overlapped, we can keep CPU cores busy. Besides TreeServer, we have developed two other systems based on Tsinker's task-based computing model. The first one is Gsyncer, which is a distributed programming framework for writing subgraph finding algorithms, such as dense subgraph mining and subgraph matching, and the resulted works have been published in top venues such as VLDB, ICDE, and the VLDB Journal. The second system is Prefix FPM, which is a parallel programming framework for mining frequent patterns of any user-specified type, such as subsequences, subgraphs, subtrees, or even submatrices. The resulted work have been published in top venues such as VLDB, ICDE, and TOS. Next, let's take a look at our design of TreeServer. Initially, our data table is stored on Hadoop distributed file system organized in column major order. TreeServer adopts a master workers architecture where the columns are loaded into the memory of different workers. Each column has multiple replicas in different workers for fault tolerance and to provide more worker candidates in taking column-related tasks to improve load balancing. End users specify their model requirements and submit them as jobs to the master of TreeServer, which disassembles these models into individual trees to build with the help of workers, and which finally reassembles the constructed trees into the requested ensemble models. The master controls the pace of tree building to make sure that the memory consumption is bounded. Specifically, it only allows a fixed number of trees to be active under construction, and a new tree starts its construction only if some existing tree is fully constructed with the result is released. We have two kinds of tasks in TreeServer. Once the number of training rows falling to a node is large, we let the workers collaborate to compute the overall best split condition, and the worker tasks here are column tasks, which are network intensive. Once the number of rows falling to a node is small enough, we let a particular worker collect all these raw data from other workers into its own memory, so that the worker can construct the entire subtree under the node without communication, which is CPU intensive. We call the worker that is assigned to construct the subtree under a node as a key worker of that node. Since column tasks are IO bound and the subtree tasks are CPU bound, we would like them to coexist to keep both network and CPU cores busy simultaneously. For this reason, the master adopts a BFS and DFS hybrid method to schedule tasks. Initially, tasks for building the top-level tree nodes are scheduled in BFS manner to create enough parallelism. Once a node has a number of rows below 80,000, the tasks for the node in its subtree are then scheduled in depth-first manner so that subtree tasks can be reached sooner than BFS. Moreover, if the number of rows at a node is below 10,000, the building of the entire subtree is treated as a subtree task for compute-intensive processing by some key worker, and this process goes on. In TreeServer, there are two kinds of communication channels. One is between master and workers, which sends the task control messages from the master and sends the computed task results towards the master. The other is between workers to collect data from each other, as is needed by the key workers of subtree tasks. Next, we consider the components inside the master. The master keeps a main thread that fetches pending tasks for worker assignment, as well as a receiving thread that receives computed task results. In this slide, we see that task 3, which is a task for node 3, is at the front of the pending task buffer, and thus will be fetched by the main thread first. Since node 3 has 300,000 rows, the main thread decides that it should be processed as column tasks. Task 3 is inserted to a task table that keeps track of the current best split condition, and the column tasks are sent to different workers to obtain the best split condition of individual columns. Assume that a split condition is sent back. The receiving thread then updates the table entry for task 3 according to that split condition. When the last split condition is received, the receiving thread obtains the overall best split condition for node 3, creates node 3 with this condition, and adds it to the corresponding tree and the construction, and removes the entry for task 3 in the task table. Using the split condition, rows of node 3 are partitioned into node 4 and node 5, which creates two new tasks 4 and 5. Since node 4 has 60,000 rows, which is below the 80,000 threshold, it should be scheduled in DFS order and is thus put to the front of the pending task buffer. In contrast, node 5 has 240,000 rows. It is scheduled in BFS order and thus appended to the tail of the pending task buffer. Next, we look at the components inside a worker machine. There is a main thread that keeps receiving the assigned tasks, a receiving thread that receives the requested data, and a pool of computing threads that are the actual workhorse of task computation. In this slide, assume that a Symmetry Task for node 6 is received. The main thread then requests column data from other workers for node 6 rows, and meanwhile inserts an entry for task 6 in the task table to wait for data collection. If the last data response is received for task 6, task 6 is then moved into the task buffer waiting for computation by an available computing thread. After a computing thread fetches task 6 and has computed the subtree rooted at node 6, this subtree is then sent back to the master. So far, we have not discussed how the rows of a node is kept with its corresponding task, which we address next. A naive solution is to keep the row indices with the task objects on the master side. In this slide, task T3 is under processing with its task object in the task table keeping the row indices for node X3. And the workers W1 and W2 currently computing the best split conditions for their columns. Now, assume that both workers have sent back their best split conditions found. Then the receiving thread of the master obtains the overall best split condition, uses it to generate T6 and T7 with their corresponding row index sets, and remove T3 from the task table. Then assume that T7 is fetched by the main thread for processing. It is put into the task table along with its indices, while the tasks assigned for node X7 are also sent along with the row index sets with 8 and 9. Here, since W2 contains the best split condition of X3, we call W2 as T3's delegate worker, and T7's parent worker, which means the delegate worker of T7's parent. We can see that the master has to keep the row indices for every tree node, and it has to send the indices along with task assignment to workers, causing master-side communication bottleneck that delays the control messages as well as creating huge memory cost as a master. Note that since W2 has a selected split condition A3, it knows how to partition the row indices into those for nodes X6 and X7. So it is more reasonable for W2 instead of the master to keep the row indices for X3. Moreover, since different nodes have different delegate workers, the memory and communication cost is well distributed among the workers. Following this idea, our solution is to let a child task directly ask the parent worker for the row indices, so that the master does not need to keep any row indices. With this scheme, let us first consider a symmetry task. Initially, the master sends the symmetry task to its selected key worker without any row indices. Then the key worker first requests the row indices for the current node X from its parent worker pa, so that it can get those entries for the target column of prediction, which is locally loaded. It also requests the column data for the attributes from other workers. These requests do not contain row indices either, and the workers obtain the row indices of node X by contacting the parent worker themselves, and get the column values for those rows back to the key worker. Note that as soon as the last row index request for node X is responded, the parent worker can release X row indices from its memory. As soon as all row index requests of X and its sibling node are served, the task object of par can be deleted from the parent worker's task table. Finally, since the key worker has got the entire data table for node X, it creates a subtree rooted at X and sends it back to the master. Next, consider the column task. Initially, the master sends the column tasks to the workers. The tasks are not sent with the row indices, so the workers need to get the row indices from the parent worker themselves. And the parent worker will delete the object for the parent node of X from its task table as soon as it serves the row indices for the last data request of node X and its sibling node. Then each worker finds the best split condition of its locally loaded columns for X rows, and it returns the best split condition back to the master. Finally, the master decides the overall best split condition for the node X and then notifies the workers to delete the task objects for X. The delegate worker of X will not delete the task object until it has served all row index requests of its two child tasks. The master also tracks the workloads of communication and computation for each assigned task and the processing, so that it can assign each next task to the proper workers to minimize the load imbalance. For more details on the worker assignment, please refer to our paper. We also use TreeServer to build the deep forest model proposed by Zhihua Zhou's group, which contains many trees to construct. Notably, each intermediate forest layer has an input of very high dimension, with thousands of data columns. To make column assignment efficient, we group columns into small subgroups, and each subgroup is assigned as the smallest unit rather than individual columns to reduce the worker assignment computation cost. On HDFS, we also optimize our data organization into block files as shown in this slide, so that we can load the row partitions and the column partitions easily for processing by different workers in parallel. Note that tree construction at each layer requires parallel column processing, while after trees are constructed, the data rows are passed into these trees in parallel for feature re-representation to prepare for the input to the next layer. Our experiments show that our TreeServer system is up to 10 times faster than existing systems such as Spark MLlib and XGBoost, and is able to construct large deep forest models efficiently. Thanks for your attention, and please feel free to contact me if you have any questions.